Yeah. Hi, everyone. Welcome to lecture 3 of Introduction to Swampland. Miguel, would you please take over the conference?
All right. Thanks a lot. Um, Thanks for coming to the last day of the lectures. Sorry about the confusion with the schedule. It was originally on Saturday. That was entirely my fault. I didn't read the emails properly. So thanks to all of you that can make it today. And so I just started discussing that in the previous lecture there were some questions regarding what is good reviews for generalized global symmetries. So I was just mentioning this one by John McCreevy. It's very nice. It's a condensed matter review, although it's focused towards condensed matter. The thing is that this language of generalized global symmetries has also been extremely useful in that context. And all of the lessons apply equally well. And one thing that is very nicely explained in this review is the fact that we were discussing last week that these generalized symmetries cannot be easily broken, cannot be broken by just adding some more terms in the Lagrangian. You actually need to have some non-local objects to break the symmetry. And then there's a more recent one, which I actually don't know that well. I haven't had time to look at it in detail. But knowing the author, I'm sure it's awesome. It's a review by Nabil Iqbal. This is quite recent. It's from July this year, so I'm sure that means it's up to date. So these two are good references for the topic of generalized symmetries. Now, before we go on with the last lecture, in which I'm going to introduce the weak gravity and the distance conjectures, there is a question by Stefan in the chat from the third exercise. CP, I'm asking whether some symmetries, are they broken or gauged or whatever? And then he's pointing out that there's a typo in the exercise. Yes, that's what I mean. CP symmetry in our universe. Could it be gauge? Could it be a spontaneously broken gauge symmetry? Could it be an exact symmetry? So I'm asking which it is. Is it a gauge symmetry or a global symmetry? Or what are the possibilities? Okay, so that's the question. So what you need to do to answer that one is to think about the standard model Lagrangian. And I suggest that you have a look at, okay, this is giving a big clue, but it's more about understanding the details of why things happen. You could look at if you go to Wikipedia, you can look for CP violating processes, okay? So that is telling you something already. Okay, look for CP violating processes in the standard model. If you're not familiar with that, it's a very important, very nice story, which is related to the answer to this question. Okay, very good. So now let's get on going with the next statement. So, broad strokes, we are discussing the flagship sort of like Swampland conjectures, ideas that we believe are generally true of quantum gravities. We support these things with black hole arguments coming from black hole physics, and then we find lots of evidence for them in concrete top-downstream compactifications. So we spent actually 2 lectures talking about no global symmetries. And in particular, how, another way of saying no global symmetries is, another way of saying this is that the limit G going to 0 of a gauge coupling cannot be coupled to gravity. Okay, we were saying that no global symmetries doesn't mean that there are no symmetries in a quantum theory of gravity. A symmetry gives you exact selection rules for, let's say, scattering processes. Now, we are not saying those things cannot happen. What no global symmetries means, as we discussed in the first lecture, is that if there is a global symmetry, so if there is an exact symmetry in quantum gravity, then it has to be a gauge symmetry. So that means there's a gauge field. So there's like some Maxwell field with a Lagrangian like this. Okay, a standard Maxwell Lagrangian. And then this thing in front of the Lagrangian is the gauge coupling of the symmetry. It's the strength of electromagnetic interactions. For instance, the electric field generated by a point particle, okay, is proportional to G squared. Okay, thank you. Over R. Okay, the electric force. Now, so what you can see from this plot, okay, is that in the limit where you send G to 0, it's like switching the electromagnetic field off. Is like going to the case where you have a selection rule, but no gauge field coupled to it. So that's like recovering a global symmetry. And we don't like global symmetries in quantum gravity. So no global symmetries in particular means that you should not be able to take the limit when G goes to 0 of a gauge coupling. Is that clear? I want someone for which this is clear to write in the, okay, perfect. Okay, good. So let me repeat. So no global symmetries doesn't mean that we have no symmetries in quantum gravity, okay? It just means that only symmetries are allowed, only allowed symmetries are gauge, okay? So the fact that they're, let me just make this a bit thinner. Yeah. So the fact that they're gauged, what that means is that the charge is an electric charge, electric type charge, is an electric type charge in the sense that it is coupled to a gauge field. If you remember from the first lecture, what we were saying is that gauge symmetries are the ones that you can measure the charge from far away, okay? And if, for instance, you have an electric particle of charge Q, okay, you can measure Q from far away just by Gauss's law, by computing the integral of the electric field on the sphere infinity. So you pick some sphere, which is very far away, you integrate the electric field on here, and that gives you the electric charge inside. Okay. So that is what an so how does that work? Well, you know, it's the usual expression. You use the expression for the electric field that comes from here, right? And so the electric charge is just equal to G. That's like the Coulomb's constant times, you know, 1 over r squared, and then there's an r squared coming from the volume element of the sphere, which cancels this thing. And so actually what you get here is G times Q. There's an electric field. This is just the expression for the electric field. Okay. And you get G times Q times 4 pi in this normalization that I'm using. Okay. So you can measure the charge far away just by computing the integral of the electric field at infinity. Now, for this argument to be true, I'm just saying something very stupid, which is that for this argument to be true, it better be that the coupling, the electromagnetic coupling, this constant G, is what appears here as the prefactor of the Lagrangian. For this argument to work, it better be that G is different from 0. Okay, so that's the only case in which that argument works. When G is equal to 0, that's like saying you have electric charge that doesn't source any electric field. You're gonna measure from far away. It's like global symmetry. Okay, so the limit G exactly equals to 0 of a gauge symmetry is a global symmetry. So because we believe there's no global symmetries in quantum gravity, G equals to 0. G should, because we believe this thing doesn't happen, then G equals to 0 should never appear. Never appear in an EFT in an EFT coupled to quantum gravity. Okay, so the gauge coupling is not something in general that you choose. Is you find some, for instance, some string theory compactifications, you compute, and some value of the gauge coupling comes out. You do a different compactification, and different value of the gauge coupling comes out. And the only thing I'm saying is that when you start doing these things in consistent quantum gravity, it can never appear that the G is exactly 0, because that would give us a global symmetry. Is that understood? Is it more clear now? Yes. So to measure global charges, what you need to do, so there's the question in the chat, which is like, okay, fine, but how do we measure global charge? You cannot measure from afar. So what you need to do in this picture is you need to take your little spaceship. You're in this rocket, you know, whatever spaceship. You need to go here and count particles. You can count them locally, but you need to go to where they are and count them. Okay, this is what happens for a global symmetry. You need to go to point by point and measure them locally. The thing that means that this that the symmetries are gauge symmetry is that you can measure them from afar with electromagnetic field. Okay, so the limit of this limit G goes to 0 of a gauge symmetry is a global symmetry, so this should never appear in effective theory coupled to gravity. Okay, fine, very good. But you know, we're not mathematicians. We're physicists, and this is a bit like a math statement. So mathematician tells you, you know, G equals 0 is not allowed. You say, okay, fine. So okay, G equals 0, exactly equals to 0, not allowed. Fine. But you're a physicist, so you know how to trick the mathematician. You then ask, okay, but what about G equals to 10 to the minus 1,000? 10,000. Is this allowed? Like, you know, this is almost a global symmetry. It's almost at the bad point. And, you know, as mathematicians, if you're a mathematician, this thing is very different from this thing. But as a physicist, you know, you do things by experiments, by measurements. There's just no way that you can distinguish these two. So it should be very, very close. So if there is a problem here, as a mathematician, you can just say, well, there's a problem here, but maybe not in the other case. But as a physicist, you should worry if there's a problem here, there should be a problem here. And indeed, by trying to push this idea, okay, by trying to ask, in which sense is G equals to the 10 to the minus 1,000 bad, you get to a heuristic. Remember, heuristic argument. So a heuristic black hole argument for a new conjecture. The weak gravity conjecture. Okay. So first, I am going to tell you what the weak gravity conjecture is, what is the statement, and then we're going to discuss how it is related to something being bad when the gauge coupling is tiny. Okay. But before I do that, okay, let me see. There's a question by Martí. You already mentioned it and I forgot, but the statement G equals 0 is not allowed. Is the reason why everything couples to gravity? Very good point. It's the other way around. If everything couples to gravity, okay, so it's the other way around, right? When you put if everything couples to gravity, then that means that G must be non-zero. Okay, so this is more general. The idea that I mentioned in the first lecture, the equivalence principle, everything is coupled to gravity. In particular, it means that things have to be coupled, but it's also not like watertight. You know, you could imagine trying to, okay, imagine the following, just, you know, for the sake of imagining, like, I don't know how it would make sense to this beyond just as an example during a lecture. But imagine that you say, this is the gauge coupling, and you say, okay, I'm going to send it to 0. Okay. So essentially, this thing is diverging, so it doesn't contribute on the path integral. But you could try to well, you could try to add other terms. You could try to have a different dependence on the action. Like since the gauge coupling is going to 0, maybe you don't need gauge invariance. So you could add terms like a to the n to the action. Okay, so it's a bit more. It's more like there's a connection, an exact connection to no global symmetries through this g going to 0. But it's true, it's part of the bigger ballpark of ideas that there should not be decoupling in gravity. Okay, very good. Okay, so what is the weak gravity conjecture? So first I'm going to tell you what it is, and then I'm going to describe what is the heuristic argument for this conjecture. A heuristic black hole argument. I am focusing on arguments for Swampland conjectures which are related to black holes, precisely because this is a course which is in the broader context of a course of quantum properties of black holes. Okay, so what is the weak gravity conjecture? Weak gravity conjecture is the statement. So this is the statement of the conjecture statement. In any quantum gravity with U1 gauge field, this is just mathematical jargon for saying like electromagnetism. So here you just have to think you have a theory which is like a theory of gravity. Okay, so there's the Einstein term for the action, and then there's also like an electromagnetic field. So you have above I wrote in differential form notation. Let me just write in the more usual notation like this. So 1/4 g squared. So you have a term like this. Okay. So the statement is in any theory of quantum gravity like this, with some finite gauge couplings g, so with g finite, there must be some particle in the spectrum which has non-zero electric charge. Okay, so this is why it's just a statement that is a particle with non-zero electric charge already not new. Well, it is, but this is what we discussed before. This is part of the completeness principle. Remember, we described that no global symmetries applied to higher form symmetries means that you must have a complete spectrum of charged particles in your theory. So in particular, there's charged particles for any charge Q. So there must be some particle in the spectrum which has charge different from 0. Okay, so that one is just come from completeness. And such that its mass, little m, satisfies mass is lower than or equal to g times m Planck. Okay, so m Planck is defined as m Planck squared is equal to 1/16 pi g as usual. Okay, in Planck units. Sorry. Let me just. So what that means is that the mass of the particle, and I'm forgetting the factor of the charge here. Okay. So what this means is that the charge, in other words, the charge to mass ratio, what is called the charge to mass ratio of the particle, okay, so that would be Q G m Planck over m. Let me call it chi. Is bigger than or equal to 1. Okay. So what the weak gravity conjecture tells you is that if you thought you could have a theory like this, just with Einstein and Maxwell, you just can't. Okay. You must also have charge states, and there is an upper bound on the mass of the charge states given by its charge. Okay. Now, this is more interesting. This is way more interesting than the no global symmetry conjecture that we were discussing before. In the last lecture, I mentioned some examples where combining the completeness principle with anomalies and supersymmetry, you got very strong constraints. But all those examples, they depend on you having supersymmetry and all, those amazing structures. In general, the no global symmetry conjecture doesn't tell you what is the mass at which the states are, the states that are charged are. This is told to you by the weak gravity conjecture. In particular, for instance, imagine you have a theory where the gauge coupling is, as we were imagining before, 10 to the minus 1,000. Then the weak gravity conjecture is telling you that the mass of this particle is less than or equal, let's say it's a particle of charge 1. Let's just pretend that Q is equals to 1. Then this is 10 to the minus 10,000 in Planck units. So it's predicting the existence of essentially very light or effectively massless charged particles, okay? So it's a new constraint on the spectrum at low energies. There's no way to get constraints like this just using quantum field theory on flat space, okay? So it's a Swampland constraint. It's a very powerful Swampland constraint. So what I will do now is I will do the same as with global symmetries. I will first tell you what is the heuristic argument for the heuristic black hole argument for the weak gravity conjecture, which connects with the no global symmetries argument that we had before in terms of black hole remnants. So we're going to do that first. Then I'm going to tell you a bit about the other side of the story. What is the stringy evidence for this conjecture? Why do we believe it's true in string theory? And finally, we are gonna discuss some of its applications to phenomenology. How can we use it to learn interesting things about particle physics phenomenology? So people in phenomenology, sometimes they write down models. They just write a model, say, well, I want to explain why, inflation is the way it is, or why the dark matter is the way it is. So I'm just going to write down some Lagrangian I like, and I'm going to try to couple it to gravity. And sometimes these couplings are obstructed by statements like the weak gravity conjecture. Okay? So I'm going to do that. But before I do that, any questions about the conjecture? About the statement itself. Is the statement understood? I am just asking, it's a very simple statement. I'm asking there must be charged particles whose mass is lower than its charge in Planck units. No questions? Very good, very good. If there's, here, excellent. Very good question from Yang. Yeah, so Yang Lei is asking, what is the BPS bound? What is the BPS bound? Okay, so it's important to keep in mind that the weak gravity conjecture, it's supposed to be true for any quantum theory of gravity, okay? So also for non-supersymmetric string theories where there might be no BPS bound. Even in supersymmetric string theories, even in supersymmetric theories, there can be U1s for which they measure a charge which is not a central charge of the BPS algebra, and then even in SUSY theories, there can be U1s for which there's no BPS bound. But as you're asking, there's many cases where the weak gravity conjecture is applying to a gauge field, which is also central charge of the supersymmetry algebra. In these cases, there is also a bound of the type n bigger than or equal to something called the central charge. Okay, so that's the BPS bound, which goes the other way as weak gravity. It lowers the mass of the particle in terms of this z, and this z is proportional to q. So it's a bit like doing a sandwich. So the BPS bound is here. In most examples where people discuss weak gravity, for instance, the examples that I will describe in this lecture, is examples with 16 supercharges in 10 dimensions, so sort of like the simple examples, the two things collide. So in some examples, for instance, it can happen that z is equal to q, g, and Planck. So on one hand, the BPS bound gives you a lower bound, the weak gravity gives you an upper bound, they coincide. What does that mean? Well, what that means in these examples is that what the weak gravity is telling you is that there absolutely must be BPS particles. You could imagine a supersymmetric theory in which there's a BPS bound, but there are no actual BPS particles. Like BPS bound is just a question that comes from the Susi algebra. Whether there is actual physical states with those masses, that depends on your theory. So what we gravity conjecture is telling you in this case is that in cases where the central charge here equals the bound coming from weak gravity, what it's telling you is that there must be BPS particles. That is the case in many systems. There are some systems which are object of current interest where you can actually have a little gap between the BPS bound and what you should have here. Okay, so the expression I wrote here, QG times M Planck, okay, is not exactly the most general thing you must put. There's a more general formulation of weak gravity, which we'll come to when you include scalar forces and other stuff. And when you take that into account, there can be theories where there is indeed a gap between the BPS bound and the extremality bound. And this condition here. And so what the gravity tells you is that, well, there's an upper bound and lower bound, and it has to be some particle whose mass lies in that range. Okay. Very good. More questions? Okay. So, okay. So why do we believe this thing is true? Well, remember, there's a heuristic black hole argument, heuristic. And this heuristic is very similar to our no global symmetries heuristic. So what was the no global symmetries heuristic? Well, we were saying if there was an exact global symmetry, then that means that there is this black hole remnants with global charge. Okay, so there's black hole remnants which have a global charge, and we don't like them having a global charge because this led to a lot of trouble. So if instead of an exact global symmetry, we have something with a gauge coupling which is very small, what do we have instead of remnants? Well, the thing that defined the remnants was that they were charged under the global symmetry. So if we are talking now about a gauge symmetry and we want to talk about states which are charged under the gauge symmetry, and we want to talk about black hole physics, we need to look at black holes with electric charge. So I'm going to consider a black hole with some electric charge, large electric charge Q, and then I'm going to ask what happens to the spectrum of these black holes as the gauge coupling becomes very small. Okay, so can anybody write in the chat the name of the generalization of Schwarzschild black hole to a charge solution, a solution which is like Schwarzschild, but which also has electric charge? Does anybody know the name for that? Rn. Very good. Reisner-Nostrum, excellent. So when you have a black hole with electric charge, there is a metric. It is called the Reisner-Nostrum metric, as you guys correctly said. So I'm going to write down here. It's a generalization of the Schwarzschild metric. In 4 dimensions, it looks like this. And where this function f, okay, I'm going to work in units with m Planck is equal to 1 to simplify my expressions. This is to m over r, and then there's a term coming from the electric charge which goes like g squared q squared over r squared. Okay, so if you only have this part, this would be like Schwarzschild, and the effect of the electric charge is just to add this little thing. Okay, so let's compute the horizons of the Reisner-Nostrum geometry. You know, so horizons are locations where f is equal to 0. Okay, so putting f equals to 0 leads us to solve a quadratic equation. In Schwarzschild, it's linear, and what you get is that there's one horizon and r equals to 2m. So is G always the fine structure constant? G is the square root of the fine structure constant. Okay, alpha is G squared over 4 pi. There's a 4 pi additional normalization factor. We are always thinking of theories where the force that we're talking about is like electromagnetism. So it's like a fine structure constant, but we might not be talking about exactly the electromagnetic force. So the G that we're talking about might be, you know, in general, it doesn't have to be the electromagnetic, the one under which the electron is charged. This could be for a variety of reasons. Maybe, we are thinking about a different quantum gravity model that is not describing our own universe, and so it has different forces, different nuances with different values of the couplings. Or, even if we are trying to describe our own universe, people sometimes talk about, for instance, in one of the big mysteries nowadays is what is dark matter. Okay, so there seems to be this thing which makes up 30% of the energy density of the universe. It's like cold matter, but we don't know what it is. And people have put forth lots of ideas for what the dark matter might be. And one popular idea is that there's some particles and there's also like some electromagnetic interactions between them. They're not mediated by our own electromagnetic force, but they are like it. They go like 1/r². This is Coulomb's law, and people say they are. There's another field, like the photon is called the dark photon, that mediates this force. So this G could be, for instance, the coupling of a dark photon, which we don't know what it is, could be very different from the electromagnetic one. Okay, good. So let me find the horizons here. In Schwarzschild, there would just be one solution, but here I have two solutions. Let me just put what the horizons are. I'm just gonna put the horizons. So there's actually, because here the equation is quadratic, you actually have two solutions, which are m plus minus m squared minus g squared q squared, like this. And so this is the location of the horizons. Okay. Yeah, we're talking about an electric light charge. Yes. So this is the location of the horizons. And if we want the horizons to exist, okay, if we want horizons to exist, we must impose then the square root must be positive. The square root argument must be positive, right? Otherwise, you get like imaginary solutions for the extremal radius. When the solutions are imaginary, if not, we have a if not, we have what is called a naked singularity. And this is a bad kind of solution that doesn't happen in string theory compactifications. There's even like a GR conjecture called cosmic censorship, saying that essentially this kind of thing doesn't happen. So we're gonna generically steer away from these guys, and we're gonna demand that we don't have naked singularities. So if we have this thing, then that means there's a lower bound on the mass of the black hole. Okay. And this bound is called the extremality bound. This bound can be recast. So I didn't put the when I was writing the Reisner-Nordstrom solution, because I didn't want to write m Plancks all over the place, I was using units in which m Plancks is equal to 1. But if I restore the m Planck, this just means g m Planck q. Okay. So what that means is that if I define the charge to mass ratio for a black hole, okay, for a Reisner-Nordstrom black hole, just like I did here for particles, what I learned is that the charge to mass ratio of a black hole, chi of a black hole, because of the extremality bound, is less than 1. So black holes go the opposite that they do for particles. Okay. These black holes, you also know they have an entropy, which is equal to the horizon area over 4 in Planck units. And this goes like m squared. So like g squared, q squared for extremal black hole. So an extremal black hole, okay, is one where you saturate this bound. If m is equal to gq, black hole is said to be extremal. Okay. So we have these black holes. They have a charge to mass ratio, which is less than 1. That's very nice. And we also know if, let's just think about the extremal ones. Extremal black hole is the one which has the most charge given its mass. So we have these black holes and they're very nice. They have some mass, they have some electric field, they have some entropy. Very nice. So now let's ask what happens to these states as G goes to 0. As G goes to 0, okay, the masses according to this formula, they start accumulating. It looks like they all it looks like naively, if you fix a charge, if you fix an integer charge, it looks like the mass of this guy goes to 0, and its entropy also goes to 0. Okay, they never really go to 0 because once the black hole reaches a mass of order Planck, you don't know what happens. But essentially, what you end up is with infinitely many stable states. Okay, which are labeled by the values of this integer charge. Okay, and they just, you know, they just have, each of them is exactly stable because it carries a conserved charge. So as G goes to 0, these black holes, the Reisner-Nordström black holes, become the black hole remnants, become the remnants of a global symmetry. So remember, when G goes to 0, we recover a global symmetry. So we should have black hole remnants. Where are the black hole remnants? They are like the limit of the Reisner-Nordström black holes in this limit. Okay? Is this clear? Because if it's clear, you guys have just bought the weak gravity conjecture. Why? Well, you know, so assume this is all like this, then we just say, well, we don't like remnants. We don't like remnants when G equals 0 because they are exactly stable. So if we think like physicists, we might want to say by continuity, okay, maybe. And by the way, this is the step right now why the argument is not really, it's just a heuristic, it's just a motivation, it's not a good argument, okay? Just like the no global symmetries motivated by heuristics was motivational, but not a very rigorous argument. Because now I cannot argue this step rigorously, I just need to say maybe, okay? So maybe this means that at least if G is very, very small, Reisner-Nordström black holes are a problem. We're essentially trying to reason by continuity. So we are saying, well, if the remnants are a problem at coupling 0, at very small coupling, it sort of like should still be around. Very good. I see a question in the chat. Why remnants are stable and can't decay by emitting charged particles? Okay. When we have the argument for the no global symmetries, we argue that the remnants were stable because they were large enough charge. It was not kinematically possible for them to decay. If you remember, if not, check the video of the first lecture. We were giving an argument that if the lightest charged particle on the remnant charge has mass m, and you find a black hole which has mass of order m Planck and a huge charge, then it kinematically just cannot decay to that many particles because the decay will violate conservation of energy. So we discussed that for the global case, but you are asking the right question. If we don't like Reisner-Nordström black holes, maybe they can decay. Maybe you can make them decay. How should we make them decay? Well, how does a charged black hole decay? Well, when you have a black hole, typically you say, oh, but black hole decays by Hawking radiation, right? So Hawking radiation makes it decay. But the Hawking radiation actually is not very efficient for a near extremal black hole. In fact, the Hawking radiation is exactly 0 when you have an extremal black hole. Sorry, I made a mistake there. Okay, so Hawking radiation won't help you. And furthermore, if you want the extremal black hole to decay, it must emit charged particles. Okay, because it has to radiate away the charge. So for the black hole to decay, okay, the process that we can imagine, okay, is you have a black hole, and then it decays. So it has charge Q, and then it decays by emitting some particle of charge Q and little mass m, and so the charge of black hole are Q Q prime equals to Q minus Q, and its mass, okay, it's related. It's slightly bigger than m prime minus m. It's just this is because of the momentum. The particle is also emitted with some momentum, so they can have a bit more energy. Okay, so you could imagine a process like this, and I think this is what Ali Manpour had in mind when he asked this question. Can this process happen? Suppose I have charged particles. I know I have charged particles because of the completeness principle. Okay, well, it turns out that for this to happen, for this process to happen, while the endpoint black hole remains subextremal. So what that means is that m prime is greater than or equal to g times q prime, so it's part of the allowed region. If we want to do this thing, okay, if we want to do this thing, then it turns out there's a kinematical constraint. Imposing conservation of energy and charge means that this cannot happen if Q and M are arbitrary. This is only possible if the decay product satisfies, or in other words, that is super extremal. And this is the weak gravity conjecture. So the motivation for weak gravity conjecture is precisely that it's there so that black holes that would be problematic have a channel to decay. Okay, have a channel which is kinematically allowed for them to decay. Proving that, finding out this kinematical constraint is part of the exercise sheet, I think is the most important problem in the whole paper, and in the whole course, in the whole problem sheet. If you're stuck with that one, so it's just writing momentum conservation, energy conservation, charge conservation, and analyzing this decay process. Okay, with all these three things. If you get stuck, you should look at the original weak gravity paper where the weak gravity conjecture was proposed. So let me just give you the exact number. So the authors are they are Arkani Hamed, Mottl, Nicolis, Vafa from 2006, and I can give you the reference. So it's HepTH. It's one of the old ones, so it's just a number 0601 001. Right? This is a good time to also mention that, you know, I'm just giving you like a crash course on weak gravity very quickly. But it's a whole subject. So, you know, I was giving you reviews on Swampland, general reviews on Swampland, but a couple of years ago, this paper appeared, 2201.08 380, which is a whole review on weak gravity conjecture. So the Swampland has gotten such a big topic that we not only have big reviews about Swampland, we also have reviews about concrete constraints, concrete Swampland constraints. And here is a review which is just about the weak gravity conjecture. It's a very nice review. You should have a look at it if you're interested in the topic. So this is a kinematic constraint which is necessary. Okay. But is this sufficient? Okay. So fine, these particles exist. How does this thing happen? How does this process take place? And here there's a question by Bernardo, which is he has the right keyword and he's asking the right question, which is, okay, how does the decay happen if Hawking radiation is switched off? So Hawking is off, but Schwinger is on. The evaporation, once you have a particle which satisfies weak gravity conjecture, so the black hole loses charge via the Schwinger effect. The Schwinger effect is another mechanism for, you could think of the Hawking radiation as a process in which the near horizon geometry of the black hole decays. So you could say that the near horizon geometry decays, the vacuum there decays. Schwinger effect is a different process by which the vacuum can decay, and it can happen for a vacuum which is permeated by an electric field. So what Schwinger originally did, he showed that if you have a constant electric field and you have a theory in which there's charged particles, and he was doing the calculation in flat space, so in flat space, there is a per production rate of particles which goes like e to the minus m squared over q times the electric field. Okay. So there's a probability that this electric field is just a quantum mechanical process, that this electric field, the electric field lines will be broken because you nucleate out of the vacuum and pair of charge carriers. Okay. So the picture that we should have in mind is that the way the black hole evaporates is like this. You have your black hole, and the black hole is charged, so it has some electric field lines that are coming out, some electric field lines. And so if there's charged particles, by the Schwinger effect, what is going to happen is that you're going to be able to break these electric field line particles by having, let's say, suppose the black hole has some charge, let's say it is positive. So then what's going to happen, okay, is that you're going to emit a particle with charge plus Q here, and then minus Q is going to be here. So this particle is going to, just like in the particle picture of Parisian Wilczek for Hawking radiation, you know, this picture you have in outreach books where you say the Hawking radiation is like two particles are produced, one falls in the black hole, the other one goes to infinity. So we have the same here, only that the particle that falls into the black hole has charge minus Q. So after that happens, the black hole has charge big Q minus little q, and then this other particle just escapes to infinity. Okay, fine. So that's the picture of how that happens. But and this goes to the point of Bernardo's question, I think. How does this get? So the Schwinger calculation and this rate that I gave you here was done for an electric field in flat space. So Schwinger was doing this calculation in the 50s, and he was interested in a big capacitor with an electric field, and he wanted to see how the electric field was discharging. But here we're not exactly interested in that. We are interested in the near horizon geometry of the black hole. We're interested in a process that happens here, close to the black hole. So the near horizon geometry of the black hole is a very particular kind of geometry. So the near horizon geometry of an extremal Reissner-Nordstrom black hole, Reissner-Nordstrom black hole, is not you know, it has to be a 4-dimensional manifold, and I am gonna forget about the angular sphere, so I'm gonna just look at things which are homogeneous on the sphere. So you know, I'm gonna say that my geometry is like some two-dimensional geometry times the S2 of the sphere of the black hole. So the geometry is not Minkowski space times S2. If it was, you could use Schwinger calculation here. Instead, it's a different kind of geometry which has negative curvature, which is called ADS. It's like anti-de Sitter space. It's a two-dimensional version of anti-de Sitter space. It's ADS2 cross S2. Okay? And so what we would need to do here is not the Schwinger effect in flat space. We need a calculation for the Schwinger effect. Schwinger per production rate, Schwinger effect, come on. Schwinger effect in ADS2. Fortunately, there is a beautiful paper by Piolin and Trust, which has the identifier HEPTH0501169, which is exactly called Schwinger effect in ADS2. We are in luck. We don't need to compute anything. We can just take the formulas from their paper. And sure enough, you get an expression which is a bit like this one. So the exponential factor, some exponential factor is a bit different. We won't care so much about that. The important thing is the exponential factor is non-zero. But it also has essentially what is called a theta term, which essentially when you plug the expression of the near horizon of the electric field of the extremal black hole becomes m squared minus q squared g squared m Planck squared. So the expression for the Schwinger effect in ADS2 has a factor that is exactly the factor that you get from the kinematic argument for the weak gravity conjecture. So the black hole only decays if there is a particle which satisfies the weak gravity conjecture. Okay. So I give a bit of a schematic presentation here, but this is the heuristic idea of how black holes decay when there is charge. Okay. Okay, so does this mean that Hawking radiation doesn't emit particles whose charge is bigger than their mass? Well, for the extremal black hole, we are in a limit where the Hawking radiation switch is off. Okay. If you were to ask the question for instead of a black hole, I like to ask the question about extremal black holes. I am entitled to, you know, there are valid black holes in the theory, so I get to ask questions about them, and they are the ones that give me interesting constraints. If you instead ask these questions about a subextremal black hole, where the mass is like strictly bigger than Q, then the Hawking radiation, there's actually, you know, the Hawking and Schwinger effects sort of mix. Okay. But you can actually emit particles which are not super extremal. So you can emit particles which have charge to mass ratio less than 1 if you're far away enough from extremality. Okay. So for those black holes, the decay can happen, not a problem, but they decay towards the extremality bound. And once they get to the extremal line, then you need to have this sort of additional effects for the black hole to decay. Okay. So the point is that this kinematic argument that I told you, the thing that I asked you to do in the exercise, really requires, it only works, you only get this constraint if you look at an extremal black hole. For extremal black hole, there's no Hawking radiation. If you want to do it for a subextremal one, then there is Hawking radiation, but you don't get this constraint. Okay, I hope that answers the question of Stefan. If not, let me know. But okay, so this is the picture. This is why we want this this sort of black holes to decay. This is the heuristic argument. So this is the heuristic. It's not a great argument, mostly because one didn't argue rigorously that something is wrong if you have many rise or neutron black holes. But there probably is something to it because the weak gravity conjecture is true in every string theory example that we know of. So at this point, I think this argument is more like food for thought and to motivate you to look for connections to weak gravity to black holes than a rigorous proof. It's certainly not as good as the heuristic argument for no global symmetries. So what I'm gonna do now is I am gonna stop here for questions. I think this is an important it's an important point to stop, I think. Then we're gonna discuss what are generalizations of weak gravity conjecture, what is the stringy evidence for it a little bit, which forms are true when there's more than one in one, and some phenomenological applications. Okay, and then in the last part of the course, we discuss the final Swampland conjecture, which is called the distance conjecture. Okay, so let me stop for questions. Are there any questions about the heuristics or about the weak gravity conjecture? Okay. Oh yeah. Could we repeat why we can forego the S2 curvature contribution to the Stringer effect? Very good. So okay. I cannot repeat because I didn't explain properly. So I just did telegraphically. So what I can do is explain better. When you take the Reisner-Nordstrom, the extremal Reisner-Nordstrom geometry, and you, so essentially, you know this picture for black holes, right? Where there's like they curve space and so on and so forth. The near horizon geometry that you get for a Reisner-Nordstrom black hole is sort of like an infinite tube. So okay, so in this point, when you have a point like this, you could picture like the sphere contribution. So there's some sphere that shrinks as you go down the throat. And what happens in the near horizon geometry of a black hole is that the sphere sort of like remains of constant size. So if you have a Reisner-Nordstrom black hole, this throat is very, very long. And down here, down the throat, you can essentially take the sphere to be constant. Okay? So what that means is that the geometry, okay, the geometry is, as I said, it's like this ADS2 space cross S2. Okay, and what you can do, what your instinct should be in a problem like this is you, if you're interested in the dynamics of some particle, a particle is described by some quantum field moving this geometry, what you do is you decompose the field in spherical harmonics, right? Because there's a sphere, so you should write an answer for your field, which is adapted to the symmetries in the problem. So you should write it as some sort of like coefficient C, L, and M, Y, L, M, theta, and phi. Okay. And then what you can do is, well, and then these coefficients here, they depend on the radial coordinate here, radial coordinate, and time only, because the angular depends on these guys. What you can do is you can then plug these ansatz into your action and then integrate over the S2, integrate over the S2. And what you get is an effective problem in which you have traded the angular coordinates by just the fact that you have these fields, but this field only depends on 2 dimensions. So you get an effective 2-dimensional problem. This technique is called dimensional reduction. It's an important technique. Okay, so at the end of the day, you just have these fields C, L, and M living in 2 dimensions, R and T. And each of these fields, you can find what is the contribution of the curvature of the S2. You're asking, what is the effect of the curvature of the S2? It's very simple. So what happens is that the curvature of the S2 gives you a term in the action, which is like this. So this is the radius. So it's like the curvature of the S2 times CLM squared. So the effect of the curvature is just giving you a mass term. Curvature is equal to a 2D mass term. Okay, so if you have a 4-dimensional particle, and let's say it has, so 4D particle of mass M, actually becomes, in the 2-dimensional language, an infinite tower of fields or particles of masses, which are, MLM squared is equal to M squared plus L plus 1 times R squared. So the role of the curvature appears on the fact that you get all these particles which have bigger and bigger masses. If they have bigger and bigger masses, their charge to mass ratios is this thing. Okay, they are getting smaller and smaller and smaller. So, you know, if you look at the spherical harmonic with very high L's, these particles are going to be very heavy and you're going to be able to forget about them. I don't care about them. So the effect of the curvature is making sure that I can forget about these particles, which have higher L and M. So in the end, I just focus on the particle which is lightest. In the end, I focus on the lightest particle, which is the one which has L equals 0. This is what is called S wave. If you remember when you studied the hydrogen atom, you have S wave, P wave, etc. And S wave was the one which is rotational symmetric, which has M0 squared equals to M squared. So it has the same mass as the 4D mass. So the effect of the curvature is just that I can forget about all the others. But in the end, the story doesn't change too much. There is another curvature you could talk about because the near horizon geometry is ADS2 cross S2. So we have the curvature of the S2, which is the one we just discussed, but this space is also curved, also has a curvature, and its curvature happens to be the same as so it happens to be related. So its curvature is also 1 over R, okay? What that curvature does, the curvature of the ADS space, is introduces a small correction here that you can find in the Piling and Trust paper. I just skipped it for ease of presentation, but it doesn't change any of these conclusions too much, okay? And in particular, it goes to 0 for a very large black hole where the curvature of the horizon is very, very small, okay? Is that okay? Good, perfect. More questions about this kinematical argument. Very good. So it's 4 p.m. So we're gonna take a 5-minute break. You can think of more questions if you want about this, and if not, I'm gonna keep on telling you about weak gravity and then the distance conjecture. Okay. Thank you. Okay. So we're back. So we were talking about the weak gravity conjecture. You might ask, well, okay. I mean, all this heuristic is very nice, but I mean, how seriously should I take it? Here's one indication that perhaps you should take it a bit more seriously, which is, you know, weak gravity conjecture was this statement that the charge to mass ratio of a particle is bigger than 1 in Planck units. But now we understand why 1 in Planck units and not 2, 3, or whatever. Because weak gravity is related to the evaporation of black holes. The statement is that there is a particle whose charge to mass ratio is the reason why 1 appears is because 1 is the charge to mass ratio of an extremal black hole. That's why it appears there. So, you know, now that we have this, there is a very natural formulation of weak gravity, which is a bit more general, which is, you know, in the theory we're just discussing Einstein-Maxwell theory. So we're just discussing like one gauge field and gravity. But in general, for instance, when one looks at string compactifications, you have more general theories. There's like, for instance, one thing that happens all the time in string theory is that when you have the Maxwell term like this G is not a constant, depends on values of some scalar fields, so called the moduli. And so there's much more general theories, many more theories. And, you know, the Reisner-Nordstrom solutions are not exactly the same in those theories. They're a bit different, okay? But because the argument we gave is actually quite general, you might expect, you know, that, well, in this case, it was just 1 because the charge to mass ratio of extremal black holes is 1. But in general, it should be that the weak gravity conjecture is just a statement that the charge to mass ratio of at least one particle on the spectrum has to be bigger than the charge to mass ratio of an extremal black hole. Okay. And the only reason why you would guess, the only reason ever why you would guess this is because of the heuristics, because you think weak gravity has to do with black hole decay, etc. So this would be your conjectural formula and would apply to a very general class of theories, which have, they might have gauge couplings that depends on moduli. They might have multiple U1s, multiple gauge fields. There might be theories where you have more than one U1 gauge field, okay? And so you would have, for instance, in the case where you have two U1 gauge fields, you would have two charges. You have GQ1, charge under the first gauge field, and GQ2. And, you would have black holes along every direction here, okay? So what you would demand is that along every direction in this charge space, there should be a particle which obeys this, okay? Guess what? This is true in every string theory example studied to date. Nobody that I met in the string community doubts the validity of the weak gravity conjecture. And some people, they really like to think in terms of black hole arguments and stuff. But honestly, most people in the community, they don't doubt it because they've studied so many string compactifications, and it is just always, always, always true for particles. Always. You find particles which have this thing. So this has led to all sorts of proofs. For instance, already in the original weak gravity paper, there was a proof or a sketch of a proof in perturbative string theory, which was worked out in more detail in 2016 papers by Heidenreich, Rice, and Rudilius. And so this kind of thing is true for every perturbative string theory model. There's a general proof. What you can actually prove in the perturbative string theory easily is that there is particles whose kind is relatively large. To prove this other thing that is exactly bigger than that of the external black holes is much more complicated and is not fully proven yet. In generality, there's papers by Heidenreich and Lotito which are working on that and making a lot of progress there. But in every concrete example, if you go one by one, where you can compute everything, this thing is always true, okay? The generalization for multiple U1s, this kind of case here, is actually quite fun to think about, okay? Because, okay, so let's draw again my two charges, G1, Q1, and G2, Q2, okay? And, for each direction in the charge lattice, for instance, so for some ratio between charges, I can look at my black holes, for instance, and ask what is the charge to mass ratio. Charge to mass ratio is now a vector here because it's now the vector given by G1, Q1, G2, Q2, M Planck divided over the mass of the black hole. For instance, for a two-charge Reisner-Nordstrom black hole, you have G1, Q1 squared plus G2, Q2 squared as the mass of an extremal black hole. So if you plot, for instance, the charge to mass ratio for these black holes, they come out to be like a circle like this. Well, okay, sorry about that. This was meant to be a circle, but a circle is clearly the limit of my drawing abilities. So this will have to do. Okay, so now the weak gravity conjecture is telling you naively that if you go in this direction, the charge lattice, there is one particle which is here. And if you go in this other one, there's another particle which is here. And if you go in this one, there's another. And if you go, it's crazy. It naively looks like it's predicting infinitely many particles. Remember, we don't like to have infinitely many particles, particularly if they're degenerate in mass, because of arguments about entropy and remnants. And certainly it doesn't happen in string compactification. So what is going on? So this was described in a paper by Clifford and Chung, where they noticed that what happens is that the weak gravity object, let's say in this general direction here, okay, does exist. but it's not a single particle state. If you have, let's say, one particle satisfies weak gravity, let me just put that in a different color so it's easier to see. Let's say you have weak gravity particles here. So there's a particle which charges where its Q1 is 0, but the Q2 is non-zero, so the particle is here. And let's say there's another one here. Okay. It turns out that along this line, you can construct states which have the charge to mass ratio for every point along this line by considering multi-particle states. What kind of multi-particle states? Well, consider you have N1 particles of the particle number 1 here. And sorry, let me just call this one 2, so it's the same as the other. And this particle 1. So you have N particle of type 1. So the mass is N1, M1 plus N2, M2. And its charge is Q1, N1 plus Q2, M2. Okay. So if you compute the charge to mass ratio vector for particles, okay, so sorry, this is what I should have written down is charge vector because it has 2 components. So it's Q1 N1, Q2. If you write down the chi, which is equal to the Q over M for all values of N1 and N2, you get states precisely living on this line. So when you have more than one U1, more than one gauge field, what happens is that there has to be particles which are super extremal enough such that their convex hull contains the black hole region. So this is something called the convex hull condition. You see, it's more stringent than with gravity because you could satisfy with gravity perhaps along this line here and along this line here, but then the states that you have here would not satisfy with gravity conjecture in each of these directions. And this convex hull condition, again, is true in string theory examples, in all string theory examples. Okay, so that's another consequence of weak gravity conjecture that people have described. Okay, there's many more things that I could tell you about the weak gravity conjecture. For instance, one important thing that I'm missing is that in perturbative string theory examples, there seems to be not just one particle which is charged. There's a whole tower of particles. So in perturbative string theory, not just, so weak gravity only demands the existence of one particle so there's not just one particle whose m is less than g times q times m Planck. What happens in examples is that for all q, there is a particle, a weak gravity particle. In other words, this formula is true if you put q equals 1, 2, 3. There's a tower of charge states. Okay, so if you plot the mass of the states versus the charge, and this is the black hole extremality bound. Okay, so there's a band of states, which all of which are here. Let me see, which way should I put it? Let's see. Q over n. So yeah, okay, so there's a band of states which are for any value of the charge, they are like here, just below the extremality bound. Okay, this is called the lattice or sublattice weak gravity conjecture. We don't have a black hole argument for this one, but you know, it seems to be the stronger statement which is true in string compactification. So it's quite interesting statement. Okay. So there's many more forms of weak gravity. Check the review. I will stop now for questions about these forms of weak gravity, but then I want to move on to the applications of weak gravity, of why is this thing useful for particle phenomenology. Okay. Any questions about this part? Yeah, okay. This part was a bit botanical, but I feel it's important to let you know of all the work, even if it's just briefly, that has been done about weak gravity conjecture and the different things that have come about related to it. Now let's do the fun thing. Fun. Phenomenology. What do I mean by phenomenology? So let's assume weak gravity conjecture and try to apply it to constrain either the standard model or beyond standard model scenarios. Ideas that people have put forth to explain different physical aspects of our own universe. So for the most of the course, I've been telling you, here's one conjecture, oh, so cool, it's true in string theory. Here's another conjecture, oh, so cool in string theory. And I can use it to prove that in string theory, blah, blah, blah. That's good. That's a nice check of Swampland conjectures. But the real meat of Swampland conjectures is that they give you a bridge between black hole physics, they come motivated with black hole physics, and you can use them to constrain low energy effective field theories that are useful in phenomenology. So let's assume the weak gravity conjecture and let's try to constrain for the standard model. Does anybody know? So the weak gravity conjecture tells you that there has to be charged particles that satisfy some bound. So for instance, if we apply the weak gravity conjecture to electromagnetism, it tells you that there has to be some particle whose mass is lower than electromagnetic coupling times m Planck. Now, electromagnetic coupling, as I was saying before, is the square root of the fine structure constant over 4 pi. Okay. Sorry, it's the other way around. The 4 pi is upstairs. Not that it matters too much what I'm going to say, but so the correct version is alpha is equal to gm squared over 4 pi. Yeah, so that's like 4 pi alpha times m Planck. Does anybody know what alpha is for electromagnetism? Can you write it in the chat? What is the value of the fine structure constant in electromagnetism? Yeah, very close to 100/37. Excellent. And can you write down in the chat what is the value of the Planck mass in, let's say, giga-electron volts? Approximately, it doesn't have to be exact. Order of magnitude. People, the Planck mass is one of the big numbers. You must know the value of the Planck mass. Okay, so who thinks? Let's make a poll. Who thinks that the Planck mass is bigger than 10 to the 10 GeV? Can you write in the chat who thinks it's bigger than 10 to the 10 GeV? Okay, who thinks the Planck mass is smaller than 10 to the 10 GeV? Has to be one or the other. Very good. It's actually, with the normalizations that I'm using, is closer to 10 to the 19 GeV. And so this is an order 1 number, and it 10 to the 19. So it's actually a bit smaller than 1. So what you get is that this thing comes out to be something like 10 to the 18 GeV. The product of the gauge coupling and the Planck mass is 10 to 18 GeV. So there has to be an electrically charged particle whose mass is less than 10 to 18 GeV. Do we know any such charged particle? Is there any charged particle in the standard model whose mass is less than 10 to 18 GeV? Well, I know one. The mass of the electron is 0.5 MeV, which is certainly smaller. So the electron satisfies weak gravity conjecture. We have post-dictic the electron. Of course, this is a bit of a joke because, you know, we already knew the electron was there and the bound is, you know, is not even tight. But there's similar things that one can do which are more interesting. For instance, remember I told you about this symmetry, B minus L, that the standard model has. And we described that it could be broken or it could be gauge. Let's assume it's gauge. If it's gauge, I was telling you the gauge coupling has to be very small. And in fact, the experimental bound is that it has to be 10 to the minus 24. Okay, so now it's more interesting because the weak gravity conjecture would predict that there has to be a particle which is charged under B minus L, which has a mass which is like 10 times, which has a mass which is 10 to the minus 24 times M Planck. So if this is 10 to the minus 24, and this is 10 to the 19 GeV, this is a tiny mass. This is less than 10 to the minus 5, 10 to the minus 5 GeV. No? I mean, 10 to the minus 5 GeV is like, it's like 10 keV. It's a number which is much more than what appears typically in particle physics. Is there any particle which is that light and it's charged under B minus L? Well, we were describing that charge under B minus L is baryon number minus lepton number, and you could go over the different particles. So, for instance, the guy charged under B is, let's say, the proton, neutron, but they have a mass which is, you know, 10 to the, you know, it's like 1 GeV essentially. And examples of particles like this is the of leptonic particles is the electron, which we said has 0.5 MeV, which is bigger than this. But there's another particle which is charged under this, the neutrino. Now we don't know what the masses of the neutrinos are exactly. We know they must have mass because there's neutrino oscillations, and we have an upper bound because of the neutrino oscillations on the mass of the lightest neutrino. So there has to be a neutrino whose mass is lower than 0.03 electron volts. So given all of this, in particular, you can try to push this down a little bit. As long as the GB minus L is between 10 to the minus 30 and 10 to the minus 24, well, this comes from experiments, and this comes from weak gravity. You could say that the neutrino is the weak gravity particle. If the gauge coupling of B minus L is smaller than 10 to the minus 30, so if all those processes that, you know, all these searches for fit forces that we're talking about can push now the experimental bound is 10 to the minus 24, if they can push it here, and the particle is gauged, then we're predicting a new particle, a new leptonic particle, which could be quite interesting. Okay. But it gets even more interesting than that. In a model like this, where P minus L is gauged, I should mention this is in a paper, all of this comes from a paper by Isabel Garcia and Nathaniel Craig, which you can find in the review. Let me just give you the number. So it's it's Nathaniel Craig, Isabel Garcia, and Seth Coren. Its number is called the weak scale from weak gravity is 1904.08426. So another thing that you can point out is the following. It's like, well, okay, so suppose that indeed the B minus L is gauged and the neutrino is charged under suppose the neutrino is charged under B minus L and it's a weak gravity particle. Then the mass of the neutrino in the standard model is not just something that you write down in the Lagrangian. The neutrino gets masses because it has a coupling to the Higgs field. This is the neutrino mass. There is a Yukawa coupling, which is 10 to the minus 12. And there's a factor square root of 2. And this is the Higgs BEP, which is around 246 GeV. Okay. So in the standard model, the neutrino gets a mass only because the Higgs field has a vacuum expectation value. And if you take weak gravity conjecture, what you get is that if this coupling is very, very small, then to accommodate that, the Higgs BEP must be very, very small. Okay, both things go hand in hand. So what this is telling you is that if GB minus L is tiny, then V has to be much smaller than M Planck. Okay? Understanding why the Higgs BEP is so small compared to the Planck scale is called the electroweak hierarchy problem. And it's one of the most important, together with the fate of the cosmological constant, is one of the most important open problems in physics. Okay, how is this hierarchy generated? And the difficulty for the reason why the electroweak hierarchy problem is regarded as difficult is because if you write down Higgs potential and it has some mass term and some quartic term, the mass term receives UV corrections, receives quantum corrections, which go all the way to the cutoff. If the cutoff of your theory is Planck scale, you would expect to have a vacuum expectation value and a potential which has a BEP of order the Planck scale. And so it's very important, you know, usual field theory logic would suggest this, but this is not what is happening. So how is that coming about? And we need to have some new principle to understand features like this, because we are observing them in our own universe. This thing is what would come out, this prediction that the Higgs BEP is probably M Planck, is what would come out from a natural approach. Naturalness just posits that, well, you know, if you have some energy scale, every energy scale is going to be of the same order of magnitude, there's going to be similar. In here, in this reasoning, we have an argument why this thing is very, very small, because it's related in a way which is very unnatural from field theory point of view, but which is nevertheless dictated by quantum gravity consistency, to another quantity. Okay. Of course, you know, in this example, the only reason why the V is small is because the GV minus L is small. And so you could ask, you could be saying, we have only taken one problem of explaining why V is small to another problem of explaining why GB minus L is small. But actually, explaining why GB minus L is small is much easier because B minus L only receives what is called radiative corrections. So the generally describes, it only gets logarithmic corrections. Even if you have a very high cutoff, the corrections are logarithmic in the cutoff. So it never gets very, very big. It's much easier to explain where a gauge coupling is small than to explain why the Higgs BEP or the Higgs mass are small. So in that sense, Swampland ideas here help you ameliorate the problem, the electroweak hierarchy problem, which is one of the big ones. Now, this is a model. This is you know, this has some assumptions, but I think it's very interesting and it illustrates the power that Swampland ideas can have on low energy physics. It's very cool. You're trying to solve some of the problems that appear in low energy physics using insights that you learn from black holes. Finally, to give you another example, and with this I'll finish with gravity conjecture and move on to distance conjecture. Just like, you know, for no global symmetries, we have no global symmetries for particles, no global symmetries for higher form symmetries. There is also weak gravity conjecture for higher form symmetries. And in this case, they tell you that the extended objects charged on their higher form gauge symmetries, like strings or membranes, must have tensions that are less of a quantity of order 1 in Planck units. Okay. In particular, there is a version of it, there's a version of weak gravity, where the charged objects are what it's called instantons. And then weak gravity tells you that there is an upper bound on the Euclidean action of these instantons, which is given by a bound like this, where, so the context where this happens is whenever you have a theory with a scalar field phi, which is periodic, so satisfies this property, and then this F is what appears here. Okay, so theories like this were proposed to give models of inflation. Okay, this for most of what is called natural inflation. So in inflation, one needs to have a scalar field which rolls for a long way, and it has a very flat potential. In models like this, you have the scalar phi, and so you can have a long range. Let me just erase this. You can have a very long range for it. Okay. So you can have a very long field range for it. And then scalar potential in these models is generated by these so-called instanton effects, which are of this form. So the potential looks like this. And then if the S is much bigger than 1, then this prefactor is very small, the potential is very tiny, and this is a good model for inflation. Okay. What the weak gravity conjecture tells you is that, because the maximum field range is given by the periodicity of the scalar, so F. So it tells you if F is bigger than or equal to 1, to M Planck, then this thing is unsuppressed, and the model does not work for inflation. So one of the first thin applications of Swampland conjectures was to use weak gravity to constrain, weak gravity conjecture to constrain models of natural inflation. These kind of models. And the constraints were actually so strong that they essentially, there's some subtleties in the argument, but they are essentially strong enough to rule most of the models out. Okay? So the Swampland ideas are making a prediction about models of inflation and stuff that we will be measuring in the near future. Okay? So I know this was a bit telegraphic, but I want to let you know that the Swampland ideas, and particularly weak gravity conjecture, is useful to constrain cosmology, is useful to constrain particle physics. Now I'm gonna spend the remainder of the time. I will spend the remainder of the time talking about the last Swampland conjecture, the distance conjecture. Stefan is asking, what is the S in the inequality? Okay, so S is what is called the instanton action. There's more details in all of this in the weak gravity review that I mentioned, and also in the original papers. If you don't know what an instanton is, you are in for a wonderful time. Learning what an instanton is one of the most fun things that you can have while learning theoretical physics. So instantons are some quantum non-perturbative effects that can generate potentials for models like this. They were first studied in the context of gauge theory, and the place to learn about instantons is a book by Sidney Coleman, which is called Aspects of Symmetry. And you should look at chapter 7 of the book. It's absolutely wonderful. Okay, and then you will find a definition of what the instanton action is. Essentially, some sort of tunnel amplitude that, in some sense, it's an object which is actually like a tunnel amplitude in quantum mechanics, but which can also be interpreted in some sense as a particle living in a Euclidean spacetime. Because in some sense, it's like a particle. This is why weak gravity tells you something about it. So that's roughly the connection. Okay. Any more questions? Okay. Weak gravity argument is based on remnants decay in Planck scale, where EFT is not working and we really don't know what's going on in Planck scale. I think this is more a question, perhaps, not so much about the pheno part that we're discussing now, but about the previous part, the derivation of weak gravity. So, and the question is roughly, I'm trying to make arguments with, when the black holes are very small, when the Rystrom Nordstrom becomes very small, how do we know what is going on here? Like maybe it's not even, there's certainly not Einsteinian gravity. How do we know that the picture of space-time works? How can we get anything? Well, it's true we don't know a lot about the details of how dynamics works once you get to those scales. But there are many things that we do know, even at that scale. For instance, even when you have a black hole which goes to the Planck scale and the black hole maybe evaporates, energy must be conserved. If the black hole is in a asymptotically flat space-time, we believe energy has to be conserved. Okay. If, and this is certainly true, you can actually prove this if your black hole is in ADS, so you can map it to energy conservation in the dual field theory. But we believe this is also true in flat space, simply because of, there's another argument. So energy is conserved. Electric charge is also conserved. Okay. These things are very bulletproof. Okay. Because and why is that? Because even though the black hole is Planckian, its mass, its charge, can be measured from very far away. So if you look about the derivations that I was giving you, for instance, when I look at what is the conditions to produce weak gravity particles, okay, first of all, you can argue with that with a large black hole, but even for a Planckian black hole, the requirement is just purely kinematical. It's just conservation of mass, conservation of energy. And these are things I can trust, even when physics is Planckian, okay? Now, what this does is motivates for you the statements, and then you go and check them in string theory compactifications, where you have a lot of control, and you check that they are true even at very low energies, okay? So that's essentially the basic logic. And this is why, even though you kind of want to talk about Planckian objects, you find ways to do so that are consistent and rigorous, okay? Any more questions? Very good, very good. So I'm going to spend the last 15 minutes of the course talking about another conjecture, the last conjecture, the distance conjecture. Now, you might say, well, why did he spend so much little time on this one? It's because this is a course which is appended to a course on quantum black holes. And the distance conjecture is a conjecture one must mention, is one of the more important and certainly the most powerful Swampland conjectures. Is the most powerful in the terms of constraining pheno, but, big but, it is the only one for which there is no black hole heuristic argument. Okay? We are working on it. Lots of people are thinking about that. It's one of the dreams in the field, sort of like coming with a black hole argument for the Swampland distance conjecture. But there is no such argument yet. Okay? So I cannot relate it to properties of black holes, so it's a bit out of place in this course. And not just even the, not just the, so the reason, for other conjectures, I told you there's black hole arguments. So other conjectures. Black hole arguments, and then string theory consistency. And they both go hand in hand to provide complementary approaches of argument for the conjecture. For the distance conjecture, this one is missing. The first one is missing. There's nothing. But I still have string theory. And so the reason why I believe the distance conjecture is true is because there's so much evidence coming from string theory. There is as much evidence for the distance conjecture than there is for the weak gravity conjecture, if not more. Okay? So that's where it comes from. Very good. So it has very strong, it only comes from string theory evidence, but it's not just the evidence, it's even the statement of the conjecture is string theory inspired. What is the okay? So Stefan is asking, what is the motivation for it if there is no heuristic argument? So the motivation for this one just comes from the fact, okay, so this is just something that has been observed to be true in every string theory compactification that we know. Now, because there's no black hole argument, one might suspect that perhaps it's just only true in string theory. If there are other quantum theories of gravity, maybe it's not true in the other quantum theories of gravity, okay? So that's one possibility. You cannot rule that out now. So this is why it's different. In some senses, if the distance conjecture is both weaker and stronger. Okay, it's weaker in the sense that the support for it, there's maybe no reason why it should be true in general, but at the same time, you will see that the consequences of it are much stronger than the others. Okay, so that's the dichotomy a little bit. So it's just string theory. Okay, I'm gonna, if you wish, you can view this last part of this last 10 minutes now of the lectures as me telling you, here's an interesting property of all string theory compactifications, which we believe maybe at some point it can be explained in terms of black hole physics, but we're not there yet. Okay, good. So what is the statement of the conjecture? So even the statement is very, very, is string theory inspired. Okay. For the weak gravity conjecture, we're considering an action which was the Einstein-Hilbert term, right? Integral of R over 16 pi G. And we were putting, you know, a gauge field, right? Now, what we're gonna do is, for the distance conjecture, we're gonna forget about the gauge field. I am erasing it. Doesn't mean it's not there. It means maybe it's there, but it doesn't play a role for my argument. Instead, what I'm going to assume is that what I have coupled to gravity is a bunch of scalar fields, okay? So I have some scalar fields. There's more than one, so they come with an index, and they have kinetic terms, okay? So they have kinetic terms like this. And in general, they have a kinetic term matrix, which is this thing here. It's just like, you know, in general, I could, in the simplest case of the scalar field, you would just put 1/2. Here, I just put this. I just put some more general tensor. Why do I do that? Well, because that's what comes out of string theory all the time. Okay, so you can see even the motivation for the Lagrangian you consider is very string theory inspired. And the important thing about the scalar is for general scalars, you could also write a mass term. You could write something like this, no? Some mass tensor. But I'm going to be assuming that the scalars are exactly massless. Okay, exactly massless scalars. Exactly massless scalar. And this is what is called a modulus. Exactly massless scalars in string theory, they're called moduli. So this is a modulus. And so you can see that why would you think about this action? Won't quantum corrections lift this moduli space and give masses even if you don't put them at tree level? Well, sure, but in string theory, you often have supersymmetric compactifications in which supersymmetry guarantees you don't get corrections. So that's what you want to talk about. Okay, and because these fields don't have a potential, they don't have a mass term, you can give them arbitrary VEPs, arbitrary vacuum expectation value to phi A. So phi A could have some value VA, and you can choose the V to whatever you want, right? When you have a mass term, which is m squared phi squared, you need to put phi to 0. Otherwise, you don't have a vacuum, don't have a rolling solution. But here you can just put whatever you like. So actually, there is a whole space of theories which are parameterized by the vacuum expectation values of these guys. So different points correspond to different vacuum expectation values. And you know, in general, so the set of all possible values, set of all possible vectors, is called the moduli space of the theory. Okay, so you can have one point, another. You can put whatever you want, and at different points in moduli space, masses of particles, of heavy particles, and couplings of the theory are different. They depend on phi. Okay, so this happens all the time in string theory, that you have a moduli space like this, and the moduli fields here, for instance, if you know string theory has internal dimensions, so what happens is that there are different internal dimensions. Some of them become bigger, some of them become smaller, and the sizes and shapes of these extra dimensions are controlled by the moduli. And there's usually in a string theory compactification several moduli like this. Okay, so that's the moduli space of a theory. And one more important thing that you have is that, when you have a space like this, a space which is parameterized by some coordinates, you tend to think this space is like a manifold. And you can ask, is there a natural metric on my manifold? Like in space-time, I have the metric, space-time metric. And here I have some auxiliary space of vacuum expectation values. Do I have a natural metric there? And the answer is that you do. It's the kinetic term. So the kinetic term, if you think about it, is the tensor with two indices on the fields, like this. It's symmetric, because this thing is symmetric under exchange of A and B. And it's positive definite, because my kinetic terms have to be positive definite, otherwise I have ghost fields. So I have a symmetric, non-degenerate, positive definite matrix. That's a matrix. So I also have a metric, GAB, defined on the moduli space. Okay? And generally, when you give a VEB to some field which is much bigger than 1, then that point is at infinite distance with respect to the natural notion of distance given by the metric GAB. Okay? So we have these moduli spaces, and when one field becomes very, very large, you go to this infinite distance point. And that's what the moduli space is. So let me now give you what is the statement of distance conjecture. Pick any curve. I'm gonna draw a curve here, a blue curve. You pick any point, I call it P, and you pick a curve that goes towards the infinite distance point, like this. So this is curve gamma. And then let's pick some other point in the curve Q. So what this tells you is that the masses of particles and fields, etc. The masses of states, they are in principle different at P and Q. But what the distance conjecture tells you is that the dependence is exponential on the distance according to the metric between the points P and Q. Okay? So what it tells you is that if you draw a third axis here, which is the masses of the states, there are states whose masses go down and they approach 0, and they do so exponentially fast. And moreover, the distance conjecture tells you that there are infinitely many of these states whose masses are going to 0. Okay? So there is an infinite tower of states. So why is this conjecture important for phenomenology? Why do people care about this conjecture? The reason why they care about this conjecture is because if you are doing, you want to do, let's say, phenomenology, and you're doing effective field theory, you use an effective field theory which has finitely many fields. Maybe one of these fields is the moduli. If you crank its value to be very, very large, so whenever you have a large VEF, you're going to get into this regime. And if your effective field theory cutoff is lambda, there's going to be infinitely many states falling below your cutoff. So there's an infinite tower of states. And what that means, that for very large fields, vacuum expectation values, the effective field theory breaks down because infinite many states become light. And this can never happen in an effective field theory coupled to gravity, Effective field theory always has a finite number of physical states, okay? So, I told you this is always true in string theory. I'm gonna skip the string theory evidence. That's not gonna be important. The reason why people care about this conjecture so much, okay, is because, so people care this conjecture again constrains very heavily inflationary models. Okay, so as I told you, in inflation, you want to have a scalar, okay? You want to have a scalar field phi, which is called the inflaton. And then, this scalar must have a very flat potential for a very long field range. When you look at what the distance conjecture tells you, it tells you that you cannot have an arbitrarily large field range because there are these heavy states which are coming down. At some point, they come and put upper bounds on the field range. So there's, for instance, a paper by Scalisi and Valenzuela from 2019, where they use the distance conjecture to produce sharp bounds on inflationary observables. Okay, so just from the distance conjecture, you get sharp bounds on inflation and what can happen in models of inflation. And these are bounds on parameters that we are measuring today, things like the so-called tensor to scalar ratio, things that are going to be measured in the near future. Okay, so you're using quantum gravity principles to put bounds on observable quantities. Okay, there's many, many more things I could tell you about the distance conjecture, but we are running out of time. So let me just wrap up. Okay. So, for instance, in some of the exercises of the problem sheet, you can gain some more insight on what is the tower of states that appears in concrete string theory examples, like a compactification or perturbative string theory. So you can learn a bit more about it. There is a scenario which is motivated by the distance conjecture, which is called the dark dimensional scenario, which I think is quite exciting. One essentially uses ideas coming from the distance conjecture to argue for the existence of an extra dimension of size a few micrometers, and people are looking for this experimentally actively, so it's actually, I think, very interesting. It's very interesting part of the Swampland program, but it's not directly related to the black holes. And that is in some sense my wrap-up message. So black hole consistency at the quantum level can have implications at low energies. And those implications are part of a bigger set of things, which includes also stuff like the distance conjecture, which is called the Swampland program. And people working here, we try to understand this directly, but mostly we are interested in using this set of ideas to make testable predictions. Okay, so the end game of the Swampland program is to produce a prediction that can be checked in our lifetime. There's already several candidates, but it's an ongoing effort, really. And if you're interested, you're more than welcome to join us. Okay, there's a lot more to the Swampland. There's a lot more conjectures. For instance, there's the cover design conjecture. There's the Festina lente conjecture. There's the Gravitino mass conjecture, for instance. There's lots of people. There's many more conjectures. There's people working on proving these conjectures, on finding evidence for them, on finding new conjectures, on working out the field implications of these conjectures. So if you like it, if you're interested, you should come check out the Swampland seminars, the online Swampland seminars. If you just Google Swampland seminars, the website appears there. I'm gonna paste the link in the chat again, just in case you wanna, if you wanna have a look. And if you're interested in the Swampland, or if there's any other questions about the course or about the exercises, please do not hesitate to email me. This is my email. I'm gonna put it again. That's I'm gonna get that right because, oh, come on. I want to get that right in case there's any typo and then you guys cannot reach me. So I can be reached there for any kind of questions that you want, either about the problem, the exercises. If you ask me for anything else I can help for, I will do so, like career advice or whatever. My email is open. And so with that, I thank you for your attention. Thanks for sticking to the end. I hope you find it interesting and you learned something. And also thanks a lot to Daniel and Yashi for giving me the opportunity to speak at the beautiful course. So thanks very much.